To determine the standard potential of a reaction, we use the equation E standard is equal to E standard reduction plus E standard oxidation. From there, we determine based on the sign of E standard whether or not the redox reaction will occur spontaneously or not. E cell must be positive in order for the redox reaction to be carried out spontaneously. In choice A, assuming this is a galvanic cell, the reaction with a more positive E standard reduction is the reduction reaction. That is the case for tin. However, iron is also getting reduced. Look at the oxidation numbers. Tin is going from 4 to 2, but iron is also going from 2 to 0, which means it must have gained electrons. However, this choice does not follow the schematics of a redox reaction and can be eliminated. Since E reduction for tin is more positive than E reduction for chromium, tin must be getting reduced while chromium gets oxidized. Since this value here is E reduction, and the reverse reaction is occurring for chromium, we negate the given value, negative 0.74 volts, to positive 0.74 volts. Therefore, using the equation from earlier, we get that E standard cell is equal to 0.154, which is the E reduction for tin, and E oxidation for chromium is 0.740. And we add those together. And E standard now is 0.8944 volts. Since E standard cell is positive, this reaction must be spontaneous. For choice C, there are two reasons why we can eliminate it as an answer. First of all, if we looked purely at the E reduction values, the E standard reduction for iron 2 plus is more positive than the E standard reaction for chromium 3 plus. Therefore, in this particular reaction, we should actually see iron 2 plus getting reduced to iron. Also, another reason you can use to eliminate this choice is chromium is actually more reactive than iron, and therefore it has a greater tendency to lose its electrons. Because it has a greater tendency to lose its electrons, it should actually be getting oxidized. For choice D, we can see that both reactants are actually getting reduced. Tin is going from 4 to 2, and iron is going from 3 to 2. This does not comply with a redox reaction. Also, if you look at their standard reductions, tin actually has a less positive E standard reduction. Therefore, it should be getting oxidized while iron gets reduced. But in this case, both are getting reduced. Therefore, you can eliminate it as an answer. This last case is interesting. Although it's stoichiometry correct, as in the moles and the charges are correct, it seems to be going from one reactant to two products, and it doesn't seem to be a redox reaction. Actually, these are the two half reactions. So, based on the E reduction and using the equation we introduced previously, we get that the E standard cell is equal to negative 0.440, and we see this reaction being used right here, but it's actually the reverse reaction, so we negate the value and get negative 0.771. So, E standard is negative 1.211 volts. Since it's negative, it can't be a spontaneous reaction. Let's look at question 27. We need to know Faraday's constant for this, which is 96,500 coulombs per moles of electrons. So let's start with the time that's given to us, 10 hours. Let's convert that to seconds, 3,600 seconds per 1 hour, right? Now let's convert this time in seconds to coulombs using the amps that's given to us. So amps can also be converted to coulombs over seconds. So 30 coulombs over 1 second. Now we want to use Faraday's constant. Actually, we want to use the reciprocal. So F, because I didn't want to write the number down, over 1 mole of electrons. Now, in the compound calcium bromide, calcium has an oxidation state of 2+, but when it becomes metal, it has an oxidation state of 0. Therefore, we know there was a transfer of 2 moles of electrons when metal is produced. So, for 2 moles of electrons, we get 1 mole of calcium metal. So, now we're going to use the molar mass to find the grams of metal produced. So 1 mole of calcium over 40.078 grams. And from this, we should get the answer D. This question is asking us to calculate the free energy change for the following electrochemical cell. So, this particular line notation tells us that zinc is at the anode and copper is at the cathode, because in line notation the anode is listed first and the cathode is listed last. So, since we're being told to calculate the free energy change, we'll want to use the equation delta G is equal to negative NFE cell, with N being the electrons transferred, F being Faraday's constant, and E cell being E cell. The first thing we want to do is figure out the half reactions. From there, we can figure out E standard for the entire cell. Since zinc is at the anode and its oxidation number goes from 0 to 2, we know that it's getting oxidized. Thus, its half reaction is zinc solid becomes zinc 2 plus 2 electrons. For copper, since it's at the cathode and its oxidation number goes from 2 to 0, it's getting reduced. Its half reaction is copper 2 plus 2 electrons becomes copper solid. So, the E standard we're given for zinc is negative 0.762 volts. Since zinc is getting oxidized, we'll want to negate this value. So, for zinc, we actually have 0.762 as E standard oxidation, and the E reduction value is 0.339, and we'll want to add these together to get E standard cell, and E standard cell now we know is 1.101 volts. Since we want to find E cell and not E cell standard, we're going to have to find out Q, which is used in the Nernst equation. Now, Q is equal to the concentration of products over the concentration of reactants. In this particular reaction, the reactants are zinc solid plus copper 2 plus equals copper solid plus zinc 2 plus. Now, we don't include solids because we know that their concentrations stays the same during the reaction. So, Q is equal to zinc 2 plus, the concentration of zinc 2 plus over the concentration of copper 2 plus. From the line notation, we know that the concentration of zinc 2 plus is 1.5 and the concentration of copper 2 plus is 0.25. Therefore, Q is equal to 6. Now we have one final step until we can calculate E cell. We need to know N, which is how many moles of electrons are transferred in the overall reaction. Now, we see that zinc becomes zinc 2 plus, and that copper 2 plus becomes copper solid. Therefore, we know that N is equal to 2. Now we have all the components we need in order to solve for E cell. Now this is called Nernst equation, which we introduced earlier. So now that we've inputted all the information that we solved for earlier, we have that E cell is equal to 1.078 volts. Now we want to solve for the free energy change for this cell. So we use delta G is equal to N negative NFE cell. Now we know that N is equal to 2, and we know that F is equal to 96,500 coulombs per mole electron. And we have E cell right here. So, plugging in all the information we know, the free energy change, or delta G, for this particular cell is negative 2 moles of electrons times 96,500 coulombs per mole electron times 1.078 or E cell, and we get that the free energy change is negative 2.08 thousand joules or negative 208 kilojoules.